Alright, so we know how to write a Taylor series centered at A for some function f. And we know how to find its interval of convergence. What we haven't talked about yet and what we don't know is, does that power series actually converge to that function f? So we need to be able to think through this, we need to go back to Taylor's theorem, which was also called the remainder theorem, that said every function f of x is a sum of an nth order Taylor polynomial plus the remainder. Okay, so that p sub n of x is the nth order Taylor polynomial centered at A. And we've also talked about the fact that the remainder is equal to the n plus 1 term, which is going to be the n plus 1 derivative evaluated at point C, some value C between A and X, over n plus 1 factorial times x minus A to the n plus 1 power for C between X and A. Well, for the Taylor series to actually converge, then the remainder must approach 0 as n approaches infinity. And there's a theorem that goes into a little more detail than that. But the gist of it is, a Taylor series converges. Let me think about how I want to write this. Yeah, a Taylor series converges to function f for all x values in some interval I. The interval I is the interval of convergence. If and only if the limit as n approaches infinity of the remainder equals 0. So to determine if you've got a Taylor series that actually does converge to your function f, you find the remainder and take the limit of that as n approaches infinity. Now, it is important to note that as long as x is fixed, okay, so notice that n is approaching infinity, x isn't doing anything. If you have a limit as n approaches infinity of x to the n power divided by n factorial, that will always be 0. And that's one of those little facts that's going to come back and you're going to need it to work some problem sometime. So, write that down, circle it, highlight it, whatever you need to do so you don't forget it. So to determine if a series is going to converge, you're going to have to find the remainder and then show that the limit as n approaches infinity approaches 0. So an example real quick. Suppose we have our function f of x equals cosine x. And we're talking about the series centered at x equal pi over 2. So the first derivative is going to be negative sine of x. The second derivative is going to be negative cosine of x. The third derivative is going to be sine of x. The fourth derivative is going to be cosine x. And we could go further if we have to. We're going to need to evaluate f of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so the first derivative has a value of negative 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine pi over 2 is 0. And I don't know why I was doing that. Oh, the point. Okay, here's the point. Here's why I was doing that. Notice that each of these derivatives is going to stay between negative 1 and positive 1. So the whole point of this is to note that the absolute value of the nth derivative, or the nth plus 1 derivative, evaluated at some number c, will be less than or equal to 1. Okay, that was the point. The remainder is going to have the form Rn of x is equal to 1, because that is the maximum value for our derivative, over n plus 1 factorial times the absolute value, this would be absolute value of the remainder, times the absolute value of x minus pi over 2 to the n plus 1 power. So we want to take the limit as n approaches infinity of absolute value x minus pi over 2 to the n plus 1 power over n plus 1 factorial. Now that limit is in the same form as the limit where we had x to the n power over n factorial. Same basic form, so that limit is going to go to 0. You can certainly do some investigation with your calculator and just verify that for yourself, and that's perfectly fine. But because we show that this limit to be equal to 0, we know that the power series is going to converge for all values of x in the interval of convergence.